Hello, everyone. Thank you for joining us today and welcome to Astro 3D ECR Astronomers in Australia seminar series. My name is Anisha Harshan. I'm from the University of New South Wales in Sydney, Australia. And today I'll be chairing along with my co-chair Jielai Zhang from the Australian National University. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I'm speaking to you from the land of Beregal people, and my co-chair, Jielai, is joining from the land of Ngunnawal country. Both of our speakers are joining from the land of Wurundjeri people of Kulin Nation. We pay our respects to their elders, past and present, and extend our respect to all First Peoples joining here. All right, so why we here? This series is facilitated by Astro 3D, the Australian Research Council Centre of Excellence for All Sky Astrophysics in 3 dimensions. So COVID has, of course, affected all of our ability to travel and present at international seminars, and that has affected people in astronomers in Australia, especially because of our time zone constraints. So this series was created to provide opportunity to early career researchers in Australia to reach international audience and to try to mitigate that disadvantage. Our first speaker is Dr. Jielai Zhang from the Swinburne University of Technology, and Dr. Jielai studies transient events such as FRBs and uses multi-wavelength data as well as machine learning techniques.
Thank you, Anisha. Hi, everyone. Yeah, my name is Jielai, and I'm delighted to be talking to you today about two fast radio bursts detected during the Deeper, Wider, Faster program. Firstly, I'll talk about what fast radio bursts are, followed by a description of the Deeper, Wider, Faster program, and finally tell you about what we saw during the September 2020 observing run. So fast radio bursts are millisecond radio bursts that are so bright that they're observable over cosmological distances. What is shown here is the first ever fast radio burst ever discovered. And you can see that it is a millisecond burst that sweeps from high to low frequencies over a period of, in this case, 400 milliseconds shown on the x-axis. This dispersion is due to the delay in longer wavelength light being delayed due to electrons in the intervening space. Fast radio bursts have an isotropic spatial distribution all around us in the sky. And so far, over 160 fast radio bursts have been detected. Most of these fast radio bursts only burst once and then are never observed to repeat their burst. However, about 30 fast radio bursts have been observed to repeat by radio telescopes. So these are quite interesting, and it's an open question as to whether all fast radio bursts repeat or just a subset. Radio telescopes, many of them that have wide fields of view, do not have very good resolution enough to localize a fast radio burst. And so only 9 fast radio bursts have been localized and pinned to a position in a host galaxy. Fast radio bursts are really exciting phenomena. Their rate in the sky is higher than supernovae, and their luminosities are up to 1,000 times that of the peak luminosity of supernova 1A. And so it's a wonder that it's only recently that we've discovered their existence. And the most exciting thing is that we don't know what causes fast radio bursts. Because of the millisecond duration of fast radio bursts, or the light emitted coherently in one go, the emission region must be small, very small. And so theories that explain fast radio bursts evoke phenomena such as neutron stars and their very magnetic counterparts, magnetars. However, we don't really know how it works, and there's a lot of theories on explaining it. Fast radio bursts have only ever been observed in the radio wavelength. So there has been no observations of fast radio burst counterparts in any other parts of the electromagnetic spectrum. And it's not because we haven't tried. So let me tell you a list of all the, not all, a non-exhaustive list of all the attempts we've had to try and find fast radio burst counterparts. There has been searches for fast radio counterparts by looking for fast radio burst afterglows. That is, after a burst goes off, we flew all our telescopes of all the different wavelengths to try and see if there's any light that remains over a longer period of time than the millisecond radio burst. People have also done a little bit very recently of observing any repeating fast radio bursts as they repeat together with optical and infrared telescopes. However, these searches for fast radio burst counterparts have given no detections. More ways to search for fast radio burst counterparts is to search for FRBs following related transient time domain phenomena, such as gamma ray bursts. So there's been searches for fast radio bursts minutes or longer after observed gamma ray bursts, GRBs on this slide, as well as after gravitational wave events and superluminous supernova. There's even been searches for spatial associations with GRBs, no matter when the fast radio burst or the gamma ray burst happened. This was a search done on over 100 fast radio bursts and over 1,000 gamma ray bursts, and only one spatial association was found. The fast radio burst happened 6.5 years at the location of a gamma ray burst. But it's uncertain whether they're actually related or not. They just happen to have happened in the same direction. So all of these searches, other than this 6.5 year later spatial association, has yielded no detections either. The closest thing we've got to finding a fast radio burst counterpart in another part of the electromagnetic spectrum are two fast radio burst-like bursts from a galactic magnetar. These two bursts were preceded by two consecutive X-ray bursts 8.6 seconds beforehand. And this gap of the 8.6 seconds is consistent with the dispersion delay due to the light traveling through medium that has electrons, delaying the longer wavelength light. I said fast radio bursts like because if you look at this plot here, this is the collection of extragalactic fast radio bursts. And this is where the Galactic Magnetar radio burst sits. Don't worry too much about the X and Y axis. I'm going to draw your attention to the diagonal lines, which shows the total luminosity of the burst. And you can see that even though this burst is quite bright, it's still fainter than the faintest end of the distribution of the extragalactic fast radio bursts. The only reason that this X-ray counterpart was found for this galactic magnetar was because the X-ray telescopes and the radio telescopes happened to be looking at the same part of the sky at the same time. However, this was completely by chance. And that brings me to the Deeper, Wider, Faster program. The Deeper, Wider, Faster program is about doing this not by chance and on purpose. The Deeper, Wider, Faster program core team members are shown with our beautiful photos here. The PI of the program is Jeff Cookie, and we have two PhD students, Sarah Webb and Simon Good. We have three postdocs, myself, Dougal Dobie, and Anais Smaller, who's coming in soon, and past members are Igor and Tyler. The Deeper, Wider, Faster program coordinates observations with multi-wavelength telescopes across the whole electromagnetic spectrum. Telescopes are coordinated to observe simultaneously not only fast radio bursts, but a whole range of other sub-second to hour timescale transients. These include gamma ray bursts, flare stars, supernova shock breakouts, kilonova. So all of these things can be studied with our data. However, today I'm focusing on fast radio bursts. The telescopes that we coordinate are some of the largest in the world, going from radio. We often use the Parkes radio telescopes, but we also have used SKA precursors, ASCAP and MeerKAT. In the submillimeter, we've used the South Pole telescope. Weakest link is the infrared. However, a lot of infrared telescopes are online, so we're looking forward to that. In the visible, the main telescope we use is the 4-meter CTIO telescope, using the dark energy camera on it. In the UV, we collaborate with our Indian collaborators and use the ASTRO satellite, which also has some X-ray coverage. In the X-ray, we've often used a telescope called HXMT, provided by our Chinese partners, and in the gamma ray, we've often used SWIFT. However, this is not an exhaustive list of telescopes. We coordinate over 80 telescopes around the world in order to do this program. So the Deeper, Wider, Faster program has telescopes all around the world as well as in space, and we coordinate them to look at the same part of the sky at the same time before anything has even happened, before any burst has gone off, but also during and after. This is very different to the follow-up observation programs to find fast radio burst counterparts that I described earlier. We are on sky simultaneously with no lag and all the wavelengths, even negative lag, as we were on the field before anything has even happened. This is really important because, as we saw with the Galactic Magnetar, X-rays can arrive tens of seconds before the radio signal if it's emitted coherently. Even more excitingly, associated bursts in other wavelengths can arrive an unknown amount of time before or after a fast radio burst signal, because we really don't know what fast radio bursts are at the moment. This is a slide to show you the field of view of some of the telescopes that we use. Deeper, wider, faster. So the deeper and the wider is because we coordinate telescopes to observe and wait. It's important we have deep and wide field telescopes in order to maximize the volume probed and increase the number of events that we see. These telescopes that we choose are well matched in field of view, covering many square degrees with one pointing. So in the background, you can see our 4-meter optical telescope. In the yellow is, and this blue, many circles here are some of the radio telescopes we use. The South Pole submillimeter telescope is shown in the blue oval. And so they're very well matched. There are the high energy telescopes that we use that have even larger fields of view, including SWIFT, HXMT, and AstroSat, which are some of our space telescopes. And Pierre Auger is a cosmic ray detector that's on all the time. So we point all these telescopes at a single field of view and wait for events. We better select really good fields in order to maximize our science return. The biggest limiting factor to field selection is the ability to do simultaneous observing with the many telescopes that we coordinate position all around the world. We also like to put fast radio bursts that are known to repeat in our field to increase the chances of getting a fast radio burst detection during our observing run. I won't go into more detail on the rest, but I want to say a few more words about how do we even coordinate telescopes all around the world in order to observe the same patch of sky. It's actually not easy to know exactly what's observable with 2 known telescopes. And so here I'd like to advertise some work done by an internship student of mine, Andrews Domenyo. He's a master's student at Northwestern University in South Africa. And I think some of the audience today will know Andrews because they participated in the same summer school as him. So shout out to you all. Andrews wrote a piece of software that allows it to take information of 2 telescopes as well as the time duration that you want to observe with both telescopes. And then what is plotted, his code outputs this plot that gives you the amount of time co-observable by the 2 telescopes at every single RN deck. And so here is a plot for the Zwicky transient factory and the 4-meter CTIO telescope. And you can see that these RN decks are the best places to observe in this case. Deeper, wider, faster. What does the faster part of deeper, wider, faster program mean? Well, firstly, it's about fast cadence, so taking data with very quickly to study fast transients. And secondly, it's about doing fast discovery and fast computing in order to do prompt follow-up with spectroscopic and other telescopes. So far, I've talked a lot about one of 4 parts of the deeper, wider, faster program. And the part I've talked a lot about is the coordinated simultaneous multi-messenger observations. So these this is coordinating all the telescopes. The second part of the deeper, wider, faster program that I just alluded to is real-time data processing and transient detection. So we do this with supercomputers in real time, and we find transient candidates within minutes. This allows us to do the third part of our program, which is rapid response and conventional target of opportunity observations, where we point spectroscopic and all these other telescopes at any events we found within hours to next day. Now, some of the events we find will have time evolution over longer timescales, and so the fourth part of our program is long-term follow-up over weeks of these interesting candidates. All right, so now I will describe to you what happened in the September 2020 observing run. Before I do that, I would like to advertise again some really great work by students that were involved in this run. They're not core members of the Deeper, Wider, Faster program, but there's like 20 people I can advertise. I've prioritized advertising the students. So we've got PhD candidates here. Vivek Gupta and Junho Kim are graduating this year, and Sarah Caddy from Macquarie University will graduate next year or the year after. And Junmo Kim is at KMT-net and a young scientist as well. So watch out for them on the job market. For the September 2020 observing run, I would like to describe to you what we found for one particular field that we observed. And this field has a repeating fast radio burst in it. The field is positioned with this little yellow circle here. And what is plotted here is the extinction, that is how much dust is along the line of sight for the southern galactic pole. You can tell it's a southern galactic pole because this blob and this blob here are the large and small Magellanic Clouds, which you cannot see from in the north. During our observing run, we coordinated many telescopes to observe simultaneously over 6 half nights. So on this plot here, you can see along the x-axis is time, and there's 1, 2, 3, 4, 6 blocks because we observed for 6 half nights, and each row represents a telescope. The blue colors, which are the top few rows, are our higher energy telescopes and mostly space, so that's SWIFT, HXMT, and ASTROSAT. These green ones are our optical telescopes. We had time given to us on the 4-meter CTIO telescope. However, because of COVID, that telescope told us we're not working, and that was really sad. Luckily, KMT-net, which is a 1.6-meter telescope network, one of them is in Sliding Springs in Australia, and we use that one for our run as the main optical telescope. We also had Huntsman at ZADCO and Panetix, which are all optical telescopes. And the red ones indicate the radio telescopes we used, namely Murray-Yang, which is the new name for the Parkes radio telescope, and Molonglo. The 2 vertical black lines indicate where we detected our 2 fast radio bursts that I talked about in the title of my talk. The first one happened at the very end of the first day, and the second fast radio burst was detected at the very end of the last day. Let me tell you where they are positioned on the sky. In the background here is an optical image taken by KMT-net, and KMT-net, the telescope has 4 CCD chips shown here. Each CCD chip is 1 degree by 1 degree. And the two fast radio bursts we found are located here and here. This diamond indicates the position of the repeating fast radio burst, although we did not observe it to repeat during our observing run. This one is the fast radio burst we detected on the first night. And you can see that it's a lot grainier than the second one we detected on the last night of observing. And that's because this one had a signal to noise of 10, and this one had a crazy big signal to noise of 100. An interesting thing to note of these detected fast radio bursts is the dispersion measure. The dispersion measure is a measure of the integrated number of electrons which the radio light had to pass through to get to our telescopes. This one had a dispersion measure of almost 600. This one had a dispersion measure of almost 500. And our repeating fast radio burst is also almost 600 in dispersion measure. This is very interesting because it leans itself towards the possibility that these fast radio bursts are within a cluster environment. And so we've actually got time on the Anglo-Australian Telescope multi-object spectrograph to get spectra of lots and lots of objects in this field and see if we've found fast radio bursts in a cluster environment, which will be very fun. So this plot is showing the 6 half-night simultaneous observing that we did, but as well as a whole host of follow-up observing that we did as well, including with the South African Meerkat SKA precursor radio telescope, as well as a whole host of optical telescopes. So long story short, we did not detect any fast radio burst counterparts in our simultaneous or follow-up observing campaign, and we did not see any repeat bursts of the fast radio burst that we detected, nor the repeater in our field during follow-up. However, this does represent the most comprehensive set of multi-wavelength data that overlaps in time and sky location with not just one, but two fast radio bursts. We're expected to make a fast radio detection with future observing runs every year or two. And so hopefully after we do this a few times, we will either detect a fast radio burst counterpart or put more and more stringent limits on the...
That's 1 minute mark, sorry.
1 more minute? Anisha, did you say 1 more minute?
Yes, yes, yes. Sorry.
Okay, thanks. Yeah, so I'm excited in the future years to share with you if we do find a counterpart. Then I will end with telling you a little bit about some of the most difficult things of coordinating simultaneous multi-wavelength telescopes and things that can go wrong. So at the time of the second fast radio burst, all of our optical telescopes were clouded out. Even though they were spread around all around Australia, they were all clouded out. At the time of the first fast radio burst, our main optical telescope, it broke for 6 minutes, exactly centered on the time of the fast radio burst. That was very disappointing. And also for the first fast radio burst, the HXMT X-ray telescope was over something called the South Atlantic Anomaly, which is an area with low magnetic fields and a lot of cosmic rays, so the data is completely rubbish. So these are all things that can happen. And part of the reason why we have a network of over 80 telescopes is so that we can have redundancies and make sure if a fast radio burst does go off, then we will make sure still to have other telescopes watching. I'll leave you with this plot, which represents the most comprehensive set of multi-wavelength data that overlaps in time and sky location with not just one, but two fast radio bursts. And take any questions. Thank you.
Thank you so much, Jielai, for the great comprehensive talk. Jielai, do you see any questions?
Yeah, so cool. So we have some questions from the chat. The first question Yeah, so first question from Sarah. Sarah, do you want to ask your question by yourself?
Okay, it's just a basic one, really. I think the repeaters, the FRB repeaters. I mean, is there like a typical repeat period? Do you find most of them, repeat over this time, or there doesn't seem to be any pattern? They're all completely different.
Yeah, that's a really, really good question. I'll answer your question and then add a bit of extra interesting information. So there is only one fast radio burst with published repeating pattern. I can't remember the numbers in the name of the repeating fast radio burst, but it repeats every 16 days. And when it's on the repeating phase, that repeating phase lasts for 4 days. So that was a really exciting find. And so in the future, what would be super cool is if we know those 4 days, this repeating fast radio burst will be very active. Then we point and do a deeper, wider, faster program on that telescope. And something we're working towards, because it's in the Northern Hemisphere, something we're working towards is to make sure we have a lot of Northern Hemisphere partners. The extra bit of information, though, is even though the other fast radio bursts we don't know their repetition properties yet, what we do know is that this, many slides. If you look at this plot for the repeating fast radio bursts, they have a specific pattern that looks different to non-repeating bursts. And so there are some fast radio bursts with the repeating morphology or look that people keep staring at to see if they repeat or not, to confirm if it's actually indicative of repetition, which is also another cool bit of science. Thanks, Sarah.
Good. There's another question from Adam. Adam, do you want to ask your question?
I can ask it if so wish. My question was, based on those FRBs that you detected with DWF, if they do come from a cluster, are you able to get a rough distance estimation based on their angular separation, assuming they're either from a globular cluster or a galaxy cluster, an average size of those, to get some sort of maybe independent distance other than DM?
Yeah, so if we do find like there's a cluster there, then we'll be able to like with the redshift to all the galaxies we find with the AAT will tell us a redshift to those. But are you asking if I can do something now with like angular separation?
Based on like the angular separation on 2 of them and assume some average separation angular size of a cluster, can you get a rough distance measurement just to be separate from DM?
Yeah, I did the kind of opposite thing. I took the DM and then with the assumed upper redshift limit, and then I converted that to a distance. And if there was a cluster there, is it like the right size? And the cluster would be a bit bigger than the Coma cluster. So it's gonna have to be a gigantic cluster for this to work. Does that answer your question?
Yeah.
Okay, cool.
Do we have any other questions from the audience? Meanwhile, I can ask a quick question. So you are staring at like one piece of sky for a long time. Is there, and as I understand, there's a fair bit of gambling there. You may or may not get a FRB. So is there like a minimum number that you expect to get in the 6-day period, for example, that you are looking for?
In 6 days, we don't expect to see one, but over 2 years, if we have like 2 to 3 observing runs per year, we expect to at least see one. So I think we got very lucky that we saw 2. It should be like 0.25.
Awesome.
Yeah.
That's great. If you do not have any other questions, we should move forward to our next speaker. Thank you, Jielai, so much.